Hello everyone. This lecture is exclusively recorded for second year BSc student of BK Birla College, Kalyan. This is mathematics class, calculus paper 1. In this lecture, we will state and prove bipart rule of integration and mean value theorem of integration. So let me state and prove the biparts rule. So the statement is as follows. If f and g are two functions defined on closed interval a comma b to are differentiable function on open interval a comma b, and f dash comma g dash dash means derivative are Riemann integrable, are integrable on closed interval a comma b, then integration from a to b f into g dash is same as f of b g of b minus f of a g of a minus integration a to b f dash g. So we will prove this theorem. The proof is not difficult and algebra of Riemann integration is used. So proof. We will define a function h. So let h is a function defined on closed interval a comma b to r such that h of x is equal to f of x into g of x. F and g are differentiable, so definitely the product is also differentiable, because if two functions are differentiable, then the product is differentiable. So h is differentiable on open interval a comma b. The reason is since f and g are differentiable on open interval a comma b. So h is differentiable, so then derivative of h is h dash x is equal to, I have to use the product rule of derivative, that is f dash x g of x plus f of x into g dash x. This is true for all x belongs to open interval a comma b. Now it is mentioned that in given fact it is given that f dash and g dash are Riemann integrable. Right, so f dash is Riemann integrable, g is differentiable, differentiability implies continuity, so g is continuous. So if it is continuous, then it is going, and so let me write down this. So g is differentiable on open interval a comma b. This would imply g is differentiable on open interval a comma b. So now I want to say that sorry, I should not say differentiable, I should say it is continuous now, because differentiability implies continuity. Continuous on open interval a comma b. So yeah, just wait, let me see what I have written. F and G are differentiable, correct. So Now what I wanted to say that G is R integrable, because we have proved that a continuous function defined on a closed and bounded interval is R integrable. Now G could be, it may happen that G at, in a worst case, G may not be continuous at A and B. That could be a worst case. It may happen that it is continuous on a closed interval A comma B. But then even a function with finitely many discontinuities are integrable. That we have stated one of the theorem, that a function with finitely many discontinuity is R integrable. So here we can see that G is R integrable on closed interval A comma B. Right? Again, I am saying that it may happen that G at most A and B, it may not be continuous, but then it will be discontinuous only at A comma B, and rest all the point it is continuous. And we know that a function with finite limited discontinuities is R integrable. Right. So G is R integrable. Further, F dash is also R integrable. So F dash is R integrable. So this would imply F dash into G is R integrable by algebra of R integrability, because this result we have already proved. Product of two R integrable function is R integrable. Similarly, F into G dash. Now we know that G dash is R integrable, and is F is R integrable? Yeah, the similar technique, you can see that F is differentiable, so it is going to be continuous, so it is going to be R integrable. So since F is continuous, uh, F is differentiable on open interval A comma B, this would imply F is continuous on open interval A comma B. This would imply F is R integrable on closed interval A comma B. Also G dash is R integrable on a closed interval A comma B. This is given fact, right? So this would imply F into G dash is R integrable on closed interval A comma B. So let's call this as star. This is called as double star. So from star and double star, again we can say that the algebra is continuous. So this would imply F dash G plus F into G dash is R integrable on closed interval A comma B. So how did I got this? From star and double star. But F dash G plus F G dash, that is basically my H, because if I check what is H is basically this only, F dash G plus F G dash. So this is H only, F dash G plus F G dash. So this would imply H is R integrable on closed interval A comma B. Right. So if H is R integrable, then where is my, yeah, let me call this as some number 1. So now then I can integrate this entire one. So from 1, what I will get, integration A to B H dash x dx is equal to integral A to B f dash x gx dx plus integral a to b fx g dash x dx. Yeah, so now here h dash and derivative, so we can apply the second fundamental theorem of integral calculus. So this integration and derivative will get cancelled and it will be h of b minus h of a straight away, which is same as integral a to b f dash g plus a to b f into g dash. So by second fundamental theorem of integral calculus. But what is h of b? I know what is my h. At very initial I wrote what is h. So h of x is equal to f of x into g of x. So h of b will be f of b into g of b. H of a will be f of a minus f of a into g of a. So that I supposed to write. H of b will be f of b g of b minus f of a g of a is equal to integral a to b f dash g plus a to b f g dash. So this also I will send to this side. So what I'll get is as follows: a to b f into g dash is equal to f of b g of b minus f of a g of a minus integral a to b f dash g. I think this is what required is. We can check out this. This is what the byparts rule which I have written. So this byparts rule and what you have studied in the 12th standard, that Lie rule, they are same. So this is the same version. One can easily check that. Yeah, I think. Oh, यहाँ पर g dash वाला लिखा है क्या? What I have done is also correct. Yeah, I think it is correct. Okay, so the byparts rules is we have proved here. That's simple and not difficult at all. Now let me state and prove the mean value theorem of for the integration. So which is called as MVT. So this is for integration I am proving. So let f and g be Riemann integrable function, R integrable function on closed interval a comma b, such that g is either non-negative or non-positive throughout closed interval a comma b, and small m and capital M are infimum and supremum of f on closed interval a comma b, then there exists k belongs to small m to capital M, such that integration a to b sorry f into g is equal to k times integration a to b g. Okay, so let me prove this. So what's given, the first fact is given that f and g are Riemann integrable. Are integrable on closed interval a comma b. It is also mentioned that capital small m is the lower bound, that is infimum, and capital M is a supremum for the function f. So what does it mean is that fx lies between small m to capital M for all x, because they are one of the supremum. Supremum is one of the upper bound, and infimum is one of the lower bound. And it also said that G is either non-negative or non-positive. Is either non-negative or non-positive throughout a comma. So that means G is either greater than equal to 0 or G is strictly less than 0. That we will. So we will have this in cases. So there are 3 cases. So in case 1, if we take g of x is greater than or equal to 0 for all x belongs to closed interval a comma b. So let me explain the case if g is 0 in particular. If g of x is equal to, if g is identically 0, then what will happen with the integration? Then integration a to b f into g will be straight away this integration, since g is 0, so this is basically integral a to b 0, and 0 integration is 0, so which is same as integration k times integration a to b 0, because 0 can be written in many ways. So sorry, so which is same as k times a to b 0 is basically g. So I started with this and ended, I got this. So what I got is as follows. So integral a to b fg is equal to k times integral a to b g. So when g is equal to 0, the proof is very simple. So it is very trivial. G is equal to 0, it is trivial. So one did not have to think much. So the result holds. Now what if g is strictly greater than 0? So let me write down that. If g of x is strictly greater than 0. Okay. So since it is mentioned that fx lies between small m to capital M, we have already written this from given to, in given fact 2 we have written this, you can check that. Yeah. So what I'll do, since g is positive function, so I can multiply this with the g. So if I multiply with g of x, it doesn't affect anything on the inequality because it is strictly positive function. Right. This is true for all x belongs to closed interval a comma b. Right. And we have already proved one of the result that uh, uh, if f is less than equal to g, and if f and g both are R integrable, then integral a to b f is less than equal to integral a to b g. This we have already proved in one of the theorem, provided f and g are R integrable. So if f comma g are R integrable, so I will be using this theorem or this result over here, right? So what result I will use now, since G is R integrable, and I think we must have written G is R integrable in the given fact itself. Let me check. Yeah, I think F and G both are R integrable. It is clearly mentioned F and G are R integrable. So G is R integrable. Constant time R integrable function is again R integrable. So M times Gx is R integrable. F is R integrable. G is R integrable. So product is R integrable. I have forgotten to return here G of x. So let me write down this. Similarly, capital M is a constant, G is R integrable, so this is also R integrable. So each and every term is R integrable, so I can take integration over it. So it is integration a to b m times G of x is less than equal to integral a to b f of x into G of x dx. Here, let me write down dx less than equal to integral a to b m times G of x. Right, so this part I'm basically I don't need right now, so I can erase this part. So you can note that which function property I have used, that you can write here, that is up to you. So right now I'm not writing, one can write down here that if f is less than equal to g, then integral a to b f is less than equal to integral a to b g. This is one of the property of R integrability. Okay, so since m is a constant that can be taken outside, so m integral a to b g of x dx is less than equal to integral a to b f of x g of x d of x less than equal to capital M integral a to b g of x dx. Okay, now the next thing is that if g is strictly greater than 0, then this would imply integral a to b g is also greater than 0, because if the function is positive, then definitely it will give some positive area only, it will never be 0. So here the integration a to b g of x, this is strictly positive, so I can divide this, and this is a number. First of all, one should understand that this is one of the number. Integral a to b g of x is a number, so I can divide this entire expression by the number integral a to b g of x. So if I divide, then inequality will not change, so it will be m times less than equal to a to b. Now I'm just writing f into g, so one can write down f of x g of x, a to b. Now I'm just writing g, and I'm entirely dividing by g of x here, integral a to b g of x, and now here m, that integration will get cancelled. Right, so now what I will do, let call this term as k. Let integral a to b f into g upon integral a to b g, call this as k. If I call this as k, then what I will get is as follows: integral a to b f into g is equal to k times integral a to b g. Where does my k belongs? Because since this is k, so k lies between small m to capital M, where small m less than equal to k less than equal to capital M. Right, so we have proved if k lies there exists k between small m to capital M, such that integral a to b f into g is equal to k times f of g, a to b f. So therefore what we have proved, there exists k belongs to small m to capital M, such that integral a to b f into g is equal to k times integral a to b g. This is one of the part we have proved. So there is one more case I supposed to prove. So case 2, that if g of x is strictly less than 0. If g of x is strictly less than 0. So again I should start with this m less than equal to f of x less than equal to capital M. So I will multiply this by g, which is negative, so m times g of x. This inequality will change if you multiply with the negative sign, then the inequality changes. Capital M g of x. This is true for all x. belongs to closed interval a comma b. Now what I'll do, again that integration rule we can apply. So a to b m times g of x dx is greater than equal to integral a to b fx gx dx greater than equal to a to b m times g of x dx for all x. Now I can take this m outside, since again that's a rule, g is greater than equal to integral a to b f into g, that is again greater than equal to m times a to b g of x. Now since g is less than 0, this would imply integral a to b g is again less than 0. So because if the function is negative, the area will be contributing, it will be negative, because integration a to b g will implies an area bounded below by g of x. Okay, so I will divide this expression by now integral a to b g. So that's a negative term. When I multiply with the negative term, the inequality will, now this is greater than equal to will becomes and less than equal to a to b f into g divided by a to b g. Now this is again less than equal to capital F. So let the middle, this entire term, let me call this as k. So let k is equal to integration a to b fg upon a to b g. This would imply integral a to b f into g is equal to k times integral a to b g, where k belongs to small m to capital M. So we have seen that in the both cases there exists k between m to small m to capital M, such that integral a to b f into g is equal to k times integral a to b g. This proved. So hence proved. So we have proved the theorem, mean value theorem. So thank you for attending the lecture.